Then we are gonna see something like something called density function plot. Then we are going to analyze some transformation, the log transformation, so when we need to log transform our data. And I'm going to give you some hints about the box-Cox transformation, which is very, very powerful transformation that can solve many of your problems when the data looks like not normal or some not stationary, with some variance, not stationarity, so the variance is not constant across your observations. So, visual inspection, those are the data.
Yeah, sorry, a question from the floor. The question is, so if I have R and I follow your steps with the data from Italian Civil Protection, I could try to do this curve. It's right?
Yes, absolutely yes. The scope of this talk here, this webinar, is to make you able to do your own mathematical model, not so complicated, but still a mathematical problem able to deliver predictions. Yes. So it's just a self-contained presentation, this one here. So you can just copy or the instruction, the commands, and go to the Istituto Superiore di Sanità, so the Italian National Institute of Health, and get the data, and the program will work right away out of the box. Yes. It's very easy. And the rest of this presentation goes towards this direction. Yes. So visual inspection. The command is very easy. It's just ts.plot. Yes. Our command is this one here. ts.plot x. X is just our total positives in this case. Okay. So by writing ts.plot x in parentheses, this is exactly what you are going to get. And R gives you beautiful plots. They are usually in a high resolution. So if you see what's going on in these three circles, we can observe some anomalies here. Okay? So just by visually inspecting our time series, so x, ts.plot x, that's what's going on. And here we have to figure out something in order for us to have a better shape. So we need to correct these outliers here. I'm not going to present any correction algorithm because of the time restrictions here, but it can be easily done. Oh, why we should transform our data? Always try to do log transformation and box-Cox transformation, which I'm going to present later during my presentation. So the R command here is very easy. Log x. That's it. So log x gives my transformation, and log plot 1, where the plot 1 is just the name I gave to the transformation, of the data. That's what I get. I have a better idea of the course. Look, the total positive are here, and the total positive are here. If one look at this, and look at this, can gain less insights. According to this not log transform data, I expect something like this. According to log transform data, I expect something like this. So log transformation is a powerful transformation, which I really encourage you to consider once you have correct your data. Okay, this is the plot density. So plot density X.
Leave you a comment from the floor. Okay, now I have understand why in the newspaper there is the logarithmic transformation of data. Okay.
Oh, okay. Oh, yeah. Thank you. I appreciate that. Yeah. Sometimes yes, log is something very mathematical, and but it's very important because it gives you a better insight of the data. This is not important for anybody. It's not even for me. It's not important to know why is that. What I'm really interested in is the results, so I can get a better insight of the logarithm by using the logarithm. But it's not the whole story. Suppose that I want to plot the density. What is the density? The density is simply what's the density plot gives us the probability of a fact. So the COVID positive patients, 2,400, or 400,000, or whatever. And here, what I get. So according to what I see on the Y bar, I have the probabilities associated to each of these modalities, and usually a plot like this, so the distribution of the probabilities across my sample, okay, the distribution of the probabilities across my sample is like this, which is a kind of awful distribution because I have a bimodal distribution. It's not easy to work with this guy here. When I go and take the logarithm, of course it's not normal. Look at this heavy tail here. But if I cut this heavy tail and I can process this heavy tail using some mathematical model, what's left, gives me some idea of the real distribution of this. Here, everything is masked. Here, everything is definitely more clear. But a log transformation, so the log transformation is just part of a family, just one of a family of transformations, which includes square root, inverse, and square. So there are many transformations. So R gives you the possibility to select a box-Cox transformation. So it's just this your data is X it's your data. You take each of your data to the exponent lambda minus 1 over lambda, and lambda is the estimate of the best transformation. So when lambda is equal to 0, the right transformation is log X. When lambda is equal to 1, you don't transform the data. Lambda 0.5 is the square root. But maybe you can have something like lambda equal 0.324, which is not a square root, which is not log. It's just a lambda equal 0.345. And the R software gives you this very number, the estimate. So you just have to transform your data accordingly, which R does for you automatically. So you don't have to struggle with the transformation. And the command is, again, box ox x. So it's very, very, very easy. Now we have some minutes left. We need to introduce a parsimony principle. In statistics, there is a counterintuitive concept which says more information equals less useful information. So when I put garbage in my model, I cannot expect the model to give me good information. So but even if I don't put in garbage but good information, but too much information, the model is not going to process this big amount of information in a correct way. So this holds true even in everyday life. Too much information about something, you know, it keeps me away from giving a nice and objective judge about a movie or something. So we need not a few information, not too much. We need the right amount of information. We don't need to add the columns in our proposition. When I do my consonants, the first thing I do is following. I make a question. Please give me the fact. 2, 3 facts. When you drive your car, you need a few information. Gas, I don't know, water in the radiator. I don't need to know what's going on in the left, I don't know, gear controlling some minor mechanical part of my car. I don't need it, unless I am a mechanic, which I'm not. I just need to know the basic stuff for me to travel from point A to point B. That's it. Same goes for mathematical models. We don't need to add variables. We need the main facts. Okay? So this is a powerful model which it's very easy to implement. So regardless of the mathematics, we don't need this. It's just for presentation purposes. But if you punch ARMA X or auto.arma, auto means automatic in R, the model, the R software gives you the estimations and gives you the predictions. And what R does for you is the structure determination. So how many data back in time I need to capture to rebuild my underlying stochastic process? Okay, today is May 13. This is the positive, the estimate of the positive. So maybe I need the positive in May 12th, May 11th, May 9th, maybe just May 12th, maybe just May 11th. So how can I cut this equation? R does that for you. And this other part of the equation is called the moving average part, which I'm not going to talk about right now, but still, this part here is called MA component, so moving average components of our time series, and you know, they can be estimated quite efficiently by R in a matter of maybe 10 or 15 seconds, depending on the sample size. So those comments are what you need. Okay, suppose the model M is called, I call M a mathematical model intertrained on the variable x, the positive. So I just digit auto.arima x, and R immediately store all the information in this object M. Then we can do these two commands, autocorrelation and forecast, and everything is done. Let's do it. So auto.arma .terra int is basically the patient in ECU. So the model is of the type 1, 2, 0, and those are the forecast. So we don't need to do anything here. Auto.arma and forecast mod h equals 5. So this is the prediction horizon. So 5 points, and that's it. And that's what's going on here. So the forecasts are immediately provides at the same immediately this graph here. Very quickly, I'm going to skip this guy here because R accounts for it. We don't need it. And now let's conclude with a curve fitting approach. We need to do a visual inspection and to do log regression. So for data, epidemiological data, the command is just log regression. So we need to take the logarithms of the data and do our regression. So the command is LM, regression model. We plot them, and we use the LM on the log transform data. How? Let's see how. Here we go. So Y are our data, and X are just the time. So we don't even need to know how to interpret the output. What just we need is that if I do linear regression, the fitting is very poor. Those are my data. If I do log LM Y log X, immediately I have this graphical representation. I think we have, thank you for your attention. We have some minutes left. If some questions from the audience, I will be more than happy to answer them.
So, Livio, you explain a democratic model because everyone could try with the data available not only in Italy but in each European and world countries.
Absolutely, absolutely. And thank you, Luca, for the democratic. Yes, absolutely. Everybody. There are no crystal balls here. I am very in favor of the teamwork, but medical doctors can be autonomous in that, can be the leader of their own research, and in case of doubt, can always talk and make networks so we can connect to each other. But this is exactly what I meant. The democratic use of even of mathematical models. ARMA models are not easy. The mechanics and inside the ARMA models is quite complicated. Is differential equations, and it's something that maybe beyond the league of medical doctors, but it doesn't matter. We just need our companion R, and which is free, which is good for students, especially, or for universities, and we don't need very expensive software like other softwares, very expensive. But and R is powerful, and I believe R is very good, powerful program. Yes.
Another comment is that everybody, not also the physician, but the politics and journalists and so on, try to interpret the math equation. So a lot of people speak about logarithmic curve or epidemic or exponential and so on. But the need is of a guidance from experts. We have a comment from the floor. Is there any formula for calculation and assessment of the real number of total patients of COVID?
Yes, yes. Okay, you mean we just have a small sample of people tested for COVID, but the number of the people affected, the real number of people affected, can be only estimated. And I wrote a paper. Still is on ResearchGate and is archived too, and now it has been submitted to an important journal for peer review. And it's just this paper deals with exactly this point. So how to estimate the true inverted comma number of people affected COVID in Italy. Yes, there are formulas, and there are yes. And in this paper, by reading this paper, everybody can do that, because everything is explained step by step. Yes.
It could be useful if the European School of Oncology share the link in the Twitter, Facebook, and web pages, if it's possible.
Absolutely. That would be a pleasure and an honor. Yes.
Okay, we have no further comments from the audience. Thank you, Livio.
Thank you, Luca. Thank you for the invitation, and thank you, everybody, for the attention.
Thank you, Dr. Fenger, and thank you, Dr. Bertolucci. Ladies and gentlemen, the session has now concluded. The next TSO session will take place on the 14th of May at the same time, and Dr. Frédéric Penol-Talker of the Centre de Gene Therapy, Clermont-Ferrand, France, will discuss with Dr. Ilaria Colombo of the Oncology Institute of Southern Switzerland, Berlin-Sauna, Switzerland, the following topic: new classification of gynecological cancers. Thank you for participating, and have a pleasant evening, day, or night. Goodbye.